Welcome back. Now that we've covered the basics of audio processing and feature extraction, you might wonder, how does a computer use those features to recognize speech? Well, this is where acoustic and language modeling comes into play. Let's explain these essential mechanisms of a speech recognition system. An acoustic model aims to understand the relationship between the audio signal and phonemes. Do you recall what phonemes are? They're the smallest sound units that make up words like the b in bat or the k in cat. The acoustic model doesn't predict whole words. It focuses on recognizing the individual sound units that form them. Identifying the sequence of phonemes paves the way for understanding the complete word later. Here's how it works. It starts by extracting audio features from the signal after converting from analog to digital. Then, the model analyzes the audio features and their combinations to identify patterns and learn how they match specific phonemes and sequences. Imagine the model is learning the word cat. It begins by analyzing the first sound, k, by looking at the specific combination of audio features representing this phoneme. Then it notices how the features change as the sound transitions to a, and again as it moves to t. For example, the acoustic model may see that k has a burst of energy and specific frequency peaks. But while it moves to the a sound, the pitch and energy change smoothly, and the frequency shift. By recognizing these patterns and transitions, the model learns how each part of the word sounds and fits together, allowing it to identify cat when it hears similar audio. Now, let's move on to language modeling and its role in speech recognition. A language model uses the sequence of phonemes identified by the acoustic model to piece together the actual words and sentences being spoken. It helps the system understand which combinations of phonemes make sense as words in a given language. Here's how it works. The model estimates the likelihood of a particular sequence of words occurring. For example, after recognizing the phonemes k, a, and t, it considers which words are likely to start with these sounds, helping it choose cats over other possibilities. The model also looks at the context and grammar to determine how words fit together in a sentence. For instance, after hearing the cat, it knows that a verb is likely to follow, such as sits. So let's summarize. Acoustic models identify phonemes from the sound signal, and language models use these phonemes to construct words and sentences, ensuring the system understands the context and structure of spoken language. This collaboration between the two types of models is critical to producing accurate and natural speech recognition. Great! Now that we've explored the theory behind acoustic and language modeling, you have a solid understanding of how speech recognition systems begin to make sense of audio. In the next lesson, we'll expand on this knowledge by diving into the specific model architectures and algorithms that drive these systems. These algorithms are the engines behind the acoustic and language models, making them efficient and powerful tools for converting speech into text. This is where the real power of speech recognition comes to life. Welcome back. In the previous lesson, we explored the concepts of acoustic and language modeling. Now, let's examine the model architectures and algorithms that drive these techniques. First, we'll cover hidden Markov models, which are mainly used for acoustic modeling. Then, we'll move on to the neural networks like CNNs, RNNs, LSTMs, and transformers, which drive acoustic and language models. This journey will show how the theoretical concepts we've learned turn into practical systems for recognizing and interpreting speech. And trust me, it's plain fun to know how these systems work. You'll impress your friends with this cool knowledge. The hidden Markov models, or HMMs, are named after Andrei Markov, a Russian mathematician known for his work on probability theory. In speech recognition, HMMs represent statistical models that estimate the probability of transitioning from one phoneme to the next, while predicting the likelihood of observing certain audio features given a phoneme. How do these two estimations occur? Well, the transition probabilities of one phoneme to another are derived from analyzing a large set of labeled phoneme sequences. The model counts how often one phoneme follows another in the dataset. For example, if s is often followed by t in the data, the model assigns a higher probability to this transition. At the same time, HMMs estimate the likelihood of certain observable features occurring given a phoneme. For instance, the model learns the probability of specific frequency patterns such as a peak around 500 Hz and another around 1500 Hz, occurring when a phoneme like a is spoken. Okay, HMMs predict the next phoneme only based on the current one, not by considering the previous sequence. This approach suits acoustic modeling because speech occurs in a sequence, one sound after another. But HMMs have limitations. They cannot handle complex speech patterns like when speech speeds up, slows down, or varies in other ways, because they assume each phoneme depends only on the previous one, not the entire context. This is where artificial neural networks come into play. Neural networks can understand and process sequences of data over time. While simple machine learning models can recognize patterns, they don't consider the order of the sounds. This means they look at each sound in isolation, ignoring how the sounds change or relate to each other over time. Alternatively, neural networks analyze how each sound relates to the ones before and after, allowing them to handle variations in speech like speed and accents. They don't just look at individual sounds, they consider the entire sequence to understand the context. This makes them suitable for acoustic and language modeling. Okay. Neural networks are built using algorithms that help them learn and improve over time. To understand how they work, let's look at their structure. Neural networks are organized into layers: an input layer, one or more hidden layers, and an output layer. Consider each layer in a neural network as a group of tiny decision makers called neurons or nodes. Each neuron is connected to the neurons in the next layer and works together to process information. The connections between neurons have weights, which act like volume knobs, controlling how strong the signals passing between the neurons are. A connection's importance increases with weights and decreases when it's low. The neurons and their connections analyze the data, helping the neural network learn and make better predictions. But how exactly? It all starts with the input layer, which receives the raw data. In speech recognition, this raw data comes from audio features like MEL frequency cepstral coefficients. As a reminder, MFCCs capture critical elements of the audio signal, mimicking how our ears perceive sound. They mainly focus on frequencies that are important for speech. Imagine how each neuron in the input layer represents one of these features, supplying the network with essential details about the sound. Next, the data moves through one or more hidden layers where the processing occurs. These layers apply weights to neuron connections to analyze the input, beginning the network's pattern detection in the audio. For example, one hidden layer might identify basic sound units, like phonemes, acoustic modeling. And later layers could combine these to form words or phrases, language modeling. But how does the network learn to make better predictions? Initially, the network makes random guesses. It compares its prediction to the correct result from labeled training data to learn and improve. This data includes audio samples paired with their correct transcription. For example, if the audio contains the word cat, the training data tells the network that the expected output is cat. When the network's prediction is wrong, the system adjusts the weights. It weakens the connections that contributed to the wrong prediction and strengthens the connections that were closer to being correct. This process of fine-tuning the weights is done through an algorithm called backpropagation, which allows the network to learn from its mistakes and improve its accuracy. Finally, after several rounds of adjusting the weights, the data reaches the output layer, where the network predicts the most likely word or phoneme based on the patterns identified in the hidden layers. The flexibility of neural networks makes them highly effective for speech recognition in acoustic and language modeling. They can capture complex patterns in speech data, leading to more accurate and reliable recognition systems. But neural networks need vast amounts of data to improve, which is arguably their primary challenge. Okay, while traditional neural networks laid the basis, the arrival of deep learning has revolutionized the field of speech recognition. We'll talk about deep learning in the next lesson. See you there. Hi, let's dive into one of today's most exciting and popular subjects, deep learning. Deep learning represents neural networks with many hidden layers. This is where the term deep comes from. The increased number of layers enables the model to capture and represent complex patterns in the data, such as different variations in phonemes or accents. Deep learning models are smart enough to handle both acoustic and language modeling. They can automatically learn features from raw audio for acoustic modeling, identifying phonemes and sounds. For language modeling, they capture the structure and context of sentences. This is a big step forward. Some deep learning networks can process an audio file, waveform, or spectrogram directly, handling everything else autonomously. While traditional neural networks also learn by adjusting the weights of connections through backpropagation, deep learning models have many more layers. They can uncover deeper, more sophisticated patterns in the data. This allows them to outperform older models, especially in speech recognition where accuracy is critical. These models, however, require even larger datasets and significant computational power to train. But once trained, deep learning models can make highly accurate predictions on new unseen data. Okay, let's briefly explore some of the most popular deep learning models used in speech recognition. Convolutional neural networks, or CNNs, are a type of deep learning network designed to work with data organized in a grid, like images. This grid-like data can be considered rows and columns where each point holds a value like color or intensity. CNNs use this grid structure to detect patterns like edges and shapes, making them effective for image analysis. Convolutional neural networks are excellent for analyzing spectrograms in speech recognition because they are basically images. They can identify patterns in these spectrograms to recognize sounds like phonemes or words. CNN consists of various layers, each performing a unique role, like team members collaborating. Here's how they work together. Convolutional layers. These function as sliding windows across images or spectrograms, extracting essential details and identifying key features. Pooling layers. After pinpointing crucial details, these layers simplify the process by reducing data volume, speeding up processing, and preventing an overemphasis on trivial details. Fully connected layers. Following pattern recognition and data simplification, these layers serve as final decision makers, determining the sound's meaning, like identifying specific phonemes or words. CNNs are excellent for speech recognition because they process spectrograms, which are like pictures of sound. Their ability to break down complex data and recognize visual patterns makes them perfect for determining speech by looking at how sound frequencies change over time. By the way, if you're interested in how convolutional neural networks work, you might want to check out 365's dedicated course on CNNs. It's an excellent resource offering informative and enjoyable content. Okay, let's move on to the next type of deep learning methodology used in speech recognition: recurrent neural networks, or RNNs. RNNs are a type of deep learning network designed to process data sequentially. Simply put, they take the output from one step and use it as input for the next step. This makes RNNs perfect for recognizing speech, where understanding the order and timing of sounds, like phonemes, is essential. RNNs have a unique structure with recurrent layers that allow them to remember previous inputs. The network updates its memory, or hidden state, at every step based on the current input and previous learning. Then it uses this memory to make sense of new information. Consider an example where we're processing a sequence of phonemes in a spoken sentence, such as cat, sat, on the mat. First, the network receives the sound for the k in cat and updates its memory, or the hidden state, based on this phoneme. Next, we feed the network the sound for the a in cat. The network updates its hidden state again, but this time it uses the current phoneme a and the information it stored from the k, which helps the network understand how the first two sounds are connected. The network then processes t, updating the hidden state to capture k, a, and t, fully grasping cat. As it shifts to sat, the network updates the state with each new sound, mindful of the prior word cat. This process continues with on, the, and mat, with the hidden state accumulating information about the entire sequence of phonemes. By the end of the sentence, the hidden state contains all the information about the sounds and their order, allowing the network to better understand and predict the sequence of words based on their relationships. Okay, great. Long short-term memory, or LSTM networks, are a special kind of RNNs designed to remember information for longer periods, which is crucial for recognizing continuous speech. An LSTM network comprises units called cells which act as the network's memory. Each cell is designed to manage and store information via 3 gates. Input gate selects new information to enter the cell's memory. Forget gate identifies unneeded existing information to erase. And output gate decides which information from the memory to transmit onward. With their gates, these cells help the network remember essential details and discard irrelevant ones, making them highly effective for handling sequences in speech recognition. All right, everyone. In our next lesson, we'll dive into one of the latest breakthroughs in deep learning, transformers. I can't wait to share how they revolutionize speech recognition. See you soon. Hello, it's time to reveal the famous transformers and their use in speech recognition. You might know them as T in GPT, or Generative Pre-trained Transformer. Transformers are a deep learning model designed for processing sequential data like text and audio. Have you ever wondered why they're called transformers? They transform input sequences like audio into output sequences like text. Unlike traditional models that process sequences step by step, transformers handle the entire input sequence in parallel. This enables them to effectively capture complex dependencies in data, whether transforming speech into text, translating languages, or understanding and generating language with impressive accuracy. Let's explore their structure and see how they accomplish this task. Transformers comprise 2 main parts, the encoder and the decoder. The encoder focuses on understanding the data input, while the decoder generates the output. Let's concentrate on what this implies for speech recognition. The transformer processes an audio file by breaking it into tokens, small audio signal segments. The encoder then analyzes these tokens to identify patterns and create a detailed representation, capturing the audio's features and patterns. The decoder then takes this representation from the encoder and generates the output sequence, which is the text. It predicts words or phonemes based on the audio patterns identified by the encoder. Transformers are especially good at understanding the big picture, making them incredibly effective for speech recognition and other language-related tasks. Unlike RNNs, which process audio sequences step by step like a chain, transformers can look at the entire sequence and decide what's important, making them much better at handling long and complex audio signals. This is made possible by their renowned attention mechanism within the encoder structure. The attention mechanism assigns different weights to different parts of the input sequence, allowing the model to concentrate on the sounds or phonemes most relevant to the task. It decides which parts of the audio to pay more attention to, improving its ability to transcribe speech accurately, especially in lengthy and complex sequences. This selective focus enables transformers to handle tasks more efficiently than models that process data sequentially. Imagine you ask Amazon's virtual assistant, "Alexa, tell me a joke about data science." Here's how the transformer-based speech recognition system handles this request. Number 1. Audio input. Alexa captures your voice and breaks it into small audio segments or tokens representing different sounds. Number 2, encoder. The encoder processes these tokens to identify patterns and features like the tone and frequency of your speech. Number 3, attention mechanism. The assistant uses the attention mechanism to focus on keywords like joke and data science, helping understand the request. Decoder. The decoder then takes this processed information and generates the text command, "Tell me a joke about data science." Number 5, action execution. Lastly, Alexa responds with a joke, typically pulled from a pre-existing database in its system. Why don't data scientists trust stares? Because they're always up to something. Good to know. Transformers with their attention mechanisms have significantly improved the accuracy and efficiency of speech recognition models. They can handle longer sequences and capture context more effectively than previous models like RNNs and LSTMs. Models based on transformer architecture like Google's BERT and OpenAI's GPT have set new benchmarks in understanding and generating human language. These advancements have led to more accurate and reliable speech-to-text applications, making tasks like voice search, virtual assistants, and real-time transcription more effective. All right, we've now covered the fundamentals of transformers and their transformative impact on speech recognition. We understand how speech recognition models are structured, the algorithms they use, and the different types of features involved. I think you deserve a short break. See you soon. Hi, in this lesson, we'll explore the steps of building a speech recognition model using the knowledge obtained from the previous lessons. This additional expertise will help you understand why each phase plays a vital role in making these systems accurate and efficient. Building a speech recognition model starts with data collection. This step includes gathering a data set of audio recordings and their corresponding text transcriptions manually made by humans. Ensuring the dataset covers various accents, speaking styles, and environments is crucial for creating a robust model. Imagine a model built to recognize English speech but only trained on audio from a single region, say Texas. If someone from a different state or English-speaking country tries to use it, the model might struggle to understand what's being spoken. That's why it's crucial to include recordings from various native and non-native English speakers speaking quickly and slowly. This enables the model to recognize variations in pronunciation, allowing it to adapt to diverse voices and speaking styles, thereby enhancing accuracy for all users. After collecting the data, the crucial pre-processing steps include normalizing volume levels and eliminating background noise to improve the quality and consistency of the input data. The next step is crucial, the process of feature extraction. Here, you'll convert audio signals into meaningful features for modeling. We've discussed feature extraction, remember? Truthfully, despite its complexity, modern tools have made the process far more accessible. Many Python libraries like Librosa and PyDub provide built-in functions to extract features, such as mel-frequency cepstral coefficients and spectral contrast. These tools handle complex math behind the scenes, allowing you to focus on building and training your models without getting bogged down in the sophisticated details of signal processing. Great. After feature extraction, select a model architecture that suits both the features and your application's needs. Let's review the architectures we've discussed in previous lessons and examine the scenarios in which each would be appropriate. As discussed earlier in the course, hidden Markov models are primarily used for acoustic modeling and analyzing speech sounds. They can also perform simple sequence language modeling, such as isolated word recognition. For instance, HMMs could create a basic system for recognizing a small set of spoken commands such as start and stop. Nevertheless, hidden Markov models are rarely used for speech recognition nowadays because they pave the way for more modern techniques like neural networks. Recurrent neural networks are very efficient for sequential data and suitable for applications requiring continuous speech processing with relatively short sequences. An example can be a voicemail transcription system where the context within a single message is crucial. Long short-term memory networks are good at capturing long-term dependencies and are suitable for applications requiring understanding context over longer sequences. These can be used for a real-time speech-to-text system to transcribe sentences accurately and maintain context over longer phrases or sentences. Convolutional neural networks are helpful when applied to spectrograms or waveforms. They are particularly suitable for noise-robust feature extraction. Transformer-based models are extremely good at handling long-range dependencies and large datasets. Unlike LSTM networks, which process data sequentially and can struggle with very long dependencies, transformers use self-attention mechanisms to consider all sequence parts at once. This makes them ideal for complex applications requiring accuracy and robustness. Examples include virtual assistants like Siri and Alexa. Okay, next comes designing the model. It's common to use more than one architecture to leverage the strengths of different models for various tasks. For instance, an acoustic model might use RNNs to learn robust feature representations from the raw audio data. At the same time, RNNs or LSTM networks could handle the temporal dependencies in the speech. Additionally, transformer-based models can capture long-range dependencies and provide contextual understanding. This multi-architecture approach allows the system to learn from acoustic features effectively, while incorporating language models during post-processing to improve accuracy and context understanding. This brings us to the next crucial phase, training the model. As established practices require, we start this procedure by dividing the dataset into 3 parts: training, testing, and validation sets. Before we train the model, we often perform data augmentation. We modify the training data in various ways to make the model more robust. For instance, we might change the speed or pitch of the audio. Such modifications help the model handle different variations it might encounter in real-world scenarios. After augmenting the data, we feed it to the model, allowing it to learn from the enhanced audio features and their corresponding text. Throughout the training phase, we periodically check the model's performance using the validation set. This step ensures that the model is not merely memorizing the training data, but is also learning to generalize well to new unseen data. The next phase includes model evaluation, where we assess the model's performance using the test set. This involves measuring how accurately the model transcribes new, unseen audio data by calculating metrics, such as word or character error rate. Based on these evaluations, we can identify areas for improvement and fine-tune the model to enhance its accuracy and robustness. Now, you might wonder, does building a speech recognition model always require starting from scratch? The short answer is no. Thanks to the advancements in the field, many pre-trained models are readily available and can be fine-tuned for your specific needs. For instance, platforms like Hugging Face provide access to a wide range of pre-trained models trained on different data types, making them suitable for various purposes. You can enhance pre-trained models by fine-tuning them on your specific dataset, further refining their performance for your unique application. This way, you don't need to start from zero and can leverage existing powerful models for your project. Great! What else? The post-processing phase. Typically, text normalization is performed to convert the recognized text into a more readable form, such as expanding abbreviations, correcting punctuation, and ensuring proper capitalization. These enhancements ensure the final output is accurate, clear, and easy to understand for end users. The model deployment phase involves putting the trained speech recognition model into a real-world setting where people can use it. Optimizing the model for the specific hardware it will run on is crucial before deployment to ensure efficient performance. This may involve techniques like model quantization or converting the model to a format compatible with a target device. Once deployed, ensure it works quickly and efficiently in real time. If any issues arise or performance enhancements are needed, you're expected to update and improve the model to maintain and improve its performance over time. Alright everyone, understanding the steps of building a speech recognition model provides a solid foundation for developing effective and robust systems. This knowledge prepares us for the next lesson, where we'll explore how to select the appropriate tools for transcribing speech to text. Welcome to the last lesson from the theoretical part of the Speech Recognition with Python course. Keep up the pace and soon you'll be converting audio files to text with various tools on your own. When choosing the appropriate tool, you must ask yourself this simple question: what precisely will you do with it? Different situations require different approaches. Fortunately, various Python libraries are available to suit different needs and circumstances. To choose the most appropriate one, consider the application's or goal's complexity and scope. Simple libraries, such as Python's speech recognition, can be highly effective for tasks like converting short voice commands to text. This library is easy to use and supports multiple recognition engines, including Google Web Speech API, Microsoft Bing Voice Recognition, and IBM Speech to Text. It's ideal for scenarios requiring quick, easy integration. Furthermore, speech recognition is free, making it accessible for small projects. But it requires an internet connection and is limited in accuracy, punctuation, and API availability. More sophisticated tools could be helpful for more advanced applications, such as transcribing long audio recordings or handling diverse accents in noisy environments. Caldi, developed by Daniel Povey and a team of researchers, is a powerful open-source toolkit that provides extensive functionalities for speech recognition, including advanced acoustics, language modeling, and feature extraction. Although it requires more expertise to set up and use, Caldi is highly customizable and can be tailored to complex tasks and large-scale projects. It's designed primarily for speech recognition research and provides a flexible, extensible framework for developing state-of-the-art systems. And it's also free to use. Great! If you need a tool that can handle even more complex tasks, Deep Speech, Whisper, Wave-to-Letter, and Assembly AI are excellent choices. Deep Speech, developed by Mozilla, uses RNNs for high-quality, real-time, end-to-end speech transcription. Similarly, Meta's Wave-to-Letter++ offers deep learning solutions and is known for its speed and efficiency, making it a good fit for large datasets and applications demanding quick processing times. Both Deep Speech and Wave-to-Letter++ are open source and free to use. Whisper, created by OpenAI, is a state-of-the-art speech recognition model known for its robustness and high accuracy across various languages and accents. Whisper is particularly effective in handling background noise and varied speech patterns, making it ideal for applications in diverse and dynamic environments. And yes, it's also free. Assembly AI provides robust and flexible API-based speech-to-text services for businesses seeking easy integration and scalability. It offers features like speech diarization, sentiment analysis, and keyword extraction. Assembly AI, however, is not free, but it is worth checking out. In addition, Google Cloud Speech-to-Text, Amazon Transcribe, and Microsoft Azure Speech offer cloud-based solutions that provide high accuracy and scalability. These services are ideal for businesses that need reliable speech recognition without the hassle of managing the technical infrastructure. While they aren't free, they use pay-as-you-go pricing, which can be a cost-effective option depending on how much you use the service. Alright, let's summarize where each tool might be appropriate. Speech recognition. is ideal for simple voice command applications, small projects, and individual use, such as a home automation system that responds to basic voice commands. Caldi is suited for research projects and custom speech recognition systems in specific fields like medical transcription, which demand specific vocabulary. Deep Speech and Wave-to-Letter++ are excellent for real-time transcription services and applications needing high accuracy and speed, such as live captioning events. Whisper works well with applications in noisy or diverse environments and for multi-language transcription services, such as an app that transcribes and translates live conversations or phone calls. Google Cloud Speech-to-Text, Amazon Transcribe, and Microsoft Azure Speech are optimal for large-scale business applications and cloud-based services that require scalability and robust performance, such as customer service call transcription for a large company. Good. Later in the course, we'll explore a practical example using speech recognition and Whisper AI. We encourage you to explore all the mentioned options and discover the incredible ways to apply them. Whether the tools are free or paid, knowing their strengths and appropriate use cases will help you build exciting speech recognition applications. Perfect. We've covered the essential theory needed to understand and effectively use speech recognition. In the upcoming sections, we'll dive deeper into implementing speech recognition and transcribing audio files. Can't wait.